Okay, so we are looking at correlation analysis. Now, basically, when we talk about correlation, we are just trying to look at the nature and the degree of relationship between two variables. How are the two variables related? That is just about correlation. Do they move together? Or when one is going to the left, the other goes to the right, or we are unable to know any relationship between the two variables. So that is what we mean by correlation analysis. But what we have to understand is that correlation that doesn't mean cause and effect or causality. It's not like what we did under the regression where X causes Y. No, here we just want to know, I mean, how the variables move. Okay, it's not a matter of one causing or having a significant effect on the other. So we just want to know. So for example, we can talk about the correlation analysis of income and then savings. So when there are changes in your income, how does savings respond? So that is basically correlation analysis. Now for objectives, so please, this side is just reading and start. I'll jump a lot of things later. Those who couldn't read, you can just go back and read them, and then we rather look at the computational aspect. Okay, so for the objectives of studying correlation, why do we study correlation? Just to know the degree of relationship between the two variables. Okay, we want to know if they move together or they move in opposite directions, or there is no relationship between them at all. So if we are able to know this, then maybe we know that if there's an increase in income, we can direct the part of saving. That is if there's a correlation or there's a relationship between them. Please, 1 minute. Hello. I hope you can hear me.
Yes, sir.
All right. Sorry about that. So that is one objective of studying correlation. It also contributes to understand how economic agents behave. For example, you're a student. If you know that there's a positive correlation between the number of hours you study and your final grade, then you know that if you want a better final grade, you have to study more. Okay, you have to study more. So knowing that can shape your learning behavior. And also correlation is not just in maths and then economics or stats, but when you go to the sciences too, they also deal with correlation. So please, you find time and read all these things, like importance of correlation and all that. These are the types of correlation analysis. Okay, the types are based on one, whether the number of variables that we have in question, the number of variables that we are dealing with, or the directional relationship, and then the nature, whether it's linear or it is non-linear. For the directional relationship, we have two types. The correlation can either be positive or be negative. If it's the explanations are down there, but I'm giving the explanations here. I won't get there. Just jump. If you have a positive correlation, it means that the two variables move together. They move in the same direction. So if you have two variables, X and Y, when X is going to the right, Y is also going to the right. If X is going to the left, Y is also going to the left. When it happens like that, we say that the correlation between those two variables is positive. Then for negative, they move in opposite directions. So one goes up, the other goes down. That is on the basis of the direction. Okay, so there we have positive and then negative. Then on the basis of the number of variables that we are dealing with, we have simple correlation, partial, and then the multiple. For simple correlation, we have only two variables. We are observing only two variables, and we are using those two variables to find the correlation. So X and Y, that is all. So it's just a simple correlation between only two variables. Then for partial, we have more than two observed variables. So maybe we have X, Y, Z. Okay, more than two variables, but the correlation analysis is being done on just two. So maybe we have X, Y, Z, but we want to do a correlation analysis on only X and Y, on only X and Y. I hope you understand that. So we are not using all the observed variables. We are just taking two out of the many. That is partial correlation. Then for multiple correlation, we have more than two observed variables, and we want to know the relationship between all these variables. Okay, so please make sure you know the difference between the partial and the multiple. For multiple, we are using all the observed variables, but for partial, we are using two out of the many observed variables. So that is the types of correlation that we have on the basis of the number of variables that is being studied. Okay. Then we have linear and nonlinear. If you have two variables, X and Y, and there's a linear correlation between them, then it means that whenever one changes, there's a constant change in the other variable. So if Y is increasing and X is also increasing, you realize that the increase in X is constant. If it's 50, it's going to be 50 throughout. If it's 4, it's going to be 4 throughout. Okay, that is what we mean by linear correlation. If the correlation is not like that, then we say it is nonlinear or curvilinear. Again, most relationships that we have in reality are not linear. They are not linear. It's possible there will be a relationship, but it wouldn't be linear. So those are the types, okay? So these are just the explanations for the types, positive and negative and all that. So please, you can just go over all these ones. Right, and then we have to know the methods that we use to study correlation. Okay, we can use the scatter diagram, the graphical method, or the formulas that we later use. Okay. Now, when you have a perfectly positive correlation, okay, it means that when you draw the points for X and Y on a scatter diagram, you are able to get a straight line, which will be able to pass through all the points on the scatter diagram. Okay, if you get that straight line passing through all these points, and the gradient of that straight line is positive, that's if the straight line is moving upwards, okay, from left to right, then it means that there's a perfectly positive correlation between X and then Y. Okay, they move together, and the change is the same for X and then for Y. But then if you're able to draw the points on the scatter diagram and you get a straight line passing through all these points, but the gradient of that straight line is negative when it slopes downwards, like the normal demand curve that we know. It means that there's a negative relationship between the two. But then because you're able to draw a straight line through them, we say it's a perfect negative correlation. But in between these two perfect correlations, we have other ones too. Some are weak, some are strong, depending on the nature of the scatter diagram or the nature or the value of the correlation coefficient that you get. So let's use this. If you look at this, you see that this is almost like you can draw a straight line through all these points. And if you check the gradient of this line here, it's negative. As Y is increasing, X must fall. So there's a perfectly negative correlation. If you look at this one too, the gradient of this line is going to be positive. So as Y is increasing, you see that X2 is increasing. So there's a perfectly positive correlation. Then if you look at this one, though you can see that there's a negative relationship between the two, as y is increasing, x is increasing. But it is not possible to get a straight line through all these points. Okay, so though we have a negative relationship here, the relationship is low. Okay, the degree of that relationship is low. So we call it low or weak degree of negative correlation. And this one is a weak or a low degree of positive correlation. If you draw a scatter diagram and you get something like this, this means there's no relationship between x and y. You can't even know what happens to x when y is increasing, or what happens to x when y is decreasing. So when it happens like this, we say that there's no correlation between the two. Okay, there's no correlation between the two. So that's how we use scatter diagram to know the relationship. Please, advantages and disadvantages, you can go through those. Sorry. And then we can use the graphical method, okay, where we just draw a line through the x points and then a line through the y points. We just use a line graph. Okay, we use a line graph. After that, then we'll look at how the two lines are moving. If the two lines are moving together, then we say that there's a positive correlation. But if one is moving from left to right downwards, and the other is moving from left to right upwards, then we say that there's a negative correlation between them. So what happens is that the two lines will cross each other. When they cross each other, then we know that the relationship between them is negative. Let's use this example. These are the values of x and y, expenditure and then income for these years from 2000 to 2004. So what you have to do is that you the horizontal axis will take the years, then the vertical one will take the values of x and y. So 2000, what is the value of x? Then you mark it. 2001, what is the value of x? Then you just use a straight line to pass through all those points. Then you do same for y. Okay, you do same for y. Then you check the nature, how the lines are moving. If you look at this, the red line is for y. So from 2000 to 2004, you can see that there was an increase in y. If you check x, from 2000 to 2004, the x2 was increasing. So because of the nature of these two line graphs, we will say that there's a positive correlation between them, so that they are moving in the same direction. So that's how we use the line graph. Let's look at another example. These are the new values of x and y for years 1995 to 99. So when you draw them from 95 to 99, you realize that y was falling, but then x was what? Increasing. So this shows that there's a negative relationship between the two. One is falling, the other one is what? Is increasing. So you can either use a scatter diagram or you can use the line graph, the graphical method. Then the last one you can use are the formulas, the Pearson's product moment correlation coefficient of the Spearman's rank correlation coefficient. So that is what we want to do. Please, any question?
No, sir.
Okay. I hope you can still see the screen. Can we see the screen?
Yes, please.
Okay, so now we are looking at Pearson's and then Spearman's rank correlation coefficient. Okay, we'll look at these two and then we'll do a test of hypothesis on how significant the correlation coefficient is. So first, let's look at the Pearson's correlation coefficient. When you use the formulas, you are able to get a number, okay, a definite number that is able to measure the nature, that is the directional relationship, and two, the degree of the correlation between the variables that are being observed. So we have x and y. The r, we denote the correlation coefficient by r, as we all know. So that one, we use the sign, the coefficient. If it's negative, it talks about the nature of the relationship. If it's negative, we have a negative correlation. If it's positive, then we have a positive correlation. Then for the degree, we use the figure, the number, the magnitude of the number, okay, to know whether it is perfect, it is strong, or it is weak. So using a formula, you are able to know both the nature and then the degree. But if you take something like the graph, you can only know the nature. You can't know the degree. Okay, you can know that the variables are negatively or positively correlated, but you wouldn't really be so certain about the degree. Now, for Pearson's correlation coefficient, it's based on the assumption that one, we can only use two variables, so we need bivariate data, X and Y, and then the variables are supposed to be quantitative. They should be able to be measured. They should be able to be quantified. It's not all data. We have qualitative data. Those ones we can use the Pearson's correlation coefficient. So the data must be quantitative. Okay, the data must be quantitative. Now, this is the formula that we use for finding the Pearson's correlation coefficient. Okay, this formula here. So R equals this whole thing that we see here. The N is the number of observations. Okay, the number of observations. Sigma XY is the summation of the product of X and Y. As we all know, sigma X is the summation of the X values. Sigma X squared is the summation of the square of the X values. And sigma Y squared is the summation of the square of the Y value. So we just need to find all these terms. What I know we can all do. We just find the values of these terms, and then we just substitute them, and then we'll be able to get the value of R. Okay, we'll be able to get it. So your job here is just to know the formula. You have to know it. You just need to know the formula. Okay, the correlation coefficient is always between -1 and 1. Okay, it's from -1 and then 1. Okay, it's from -1 and 1. Please just a little. Right, so you can't have a correlation coefficient of 1.5 or -2. It's from -1 to 1. If you find the correlation coefficient and it's exactly -1, okay, if it's exactly -1, that's a perfectly negative correlation. Okay, if you get exactly -1, but if it's exactly +1, that's a perfectly positive correlation. Coefficient of 0 means there's no correlation, so there's no relationship between the two at all. Now let's look at the strong and then the weak. For strong negative correlation, the correlation coefficient must be equal to or less than -0.5. Okay, R must be less than or equal to -0.5. So if you get a correlation coefficient of say -0.65, -0.65, you see that it's less than -0.5. So that means that we have a strong negative correlation. If you have exactly -0.52, that one too shows a strong negative correlation. But then if your correlation coefficient is negative but greater than -0.5, so if you get something like -0.2 something, -0.4 something, okay, it is still negative, but it is greater than -0.5. That gives us a weak negative correlation, or at times we see low negative correlation. Okay, then for strong positive correlation, the R must be greater than or equal to 0.5, but it has to be less than 1, because as soon as it's exactly 1, we are talking about perfectly positive correlation. So R must be greater than or equal to 0. So if you get something like 0.55, 0.7, 0.9, 0.8, we are talking about strong positive correlation. Okay. And then if the correlation coefficient is positive, that's if it's greater than 0, but less than 0.5, so 0.2, 0.4, and all that, we have a positive correlation, but it is weak. Okay, so we have a weak positive correlation. I hope we understand that. All right, so this one to advantages and disadvantages, we can all do that one. So there's an example. Okay, the CEO of a factory is interested in the relationship between the production and sale of their products. The cost and sales of the various products for last year are shown below. So these are the cost and then the sales for last year. Now we have to use this data to answer these questions. What is the main purpose of investigating the relationship between sales and cost? Why do we study correlation? So that we can use it for prediction. If we know that there's a correlation between X and Y, then if X is moving in a certain direction, we can know the direction that that Y is also going to move. Okay, if we know that a correlation exists between two variables, we are able to use them for prediction. If the correlation is positive and we see that one of the two variables is decreasing, then we will know the other one to be decreasing. So the CEO wants to know this because they want to know the relationship between sales and then cost. So assuming there's a positive relationship between sales and then cost, then it means that if you want to sell more, if you want higher or higher volumes of sales, then you have to incur more cost. So you know during the production process, even if you are incurring cost, you won't worry because you know that it's going to cause an increase in sales. So that's the reason why we try to study the relationship between variables. Okay. Then the B, we have to calculate the Pearson's correlation coefficient. Okay, so we just need a formula, put it in a table form, create columns for x squared, y squared, and then xy. From there, we'll be able to find all the terms that we need in the formula. So there's a formula that we'll be using. Let's just create a table. Cost is X, sales is Y. It doesn't matter which one you use as X or Y, you still get the same answer. Okay, so it's not like the regression that we did. If you are asked to find the regression of Y on X, then you can't interchange them. Y is the dependent, X is the independent. But here we don't have any dependency. We just have two variables. There's no independent, there's no dependent. Okay, so it doesn't really matter. So now these are the observations for X, these are the observations for Y. So we need sigma X. So we have to sum the values of X, sum them up. So hopefully we are getting 64. Then we sum Y, sigma Y. This is what we have. Then we need to find the product of X and Y. So X times Y. 7 by 15, 9 by 6, 5 by 7. You do it for all the levels and then you sum it up. Okay. Then we need X squared. X squared. We square the values of X. So square all the observations and then you add them. Please, you have to verify these answers. Here, the total was 506, but when they were stating it here, they wrote 505. So please check all those things. Then Y squared, we square all the values of Y. So square them and then you sum them up. That will give you sigma Y squared. For N, you count the number of observations. Okay, count the number of observations. That will give you N. Here we are getting 10. So you just go to the formula, just insert your values. N is 10, sigma xy is there, sigma x is here, sigma y. So just insert them. Please, the square root sign is affecting all these terms. So it's not just on the first one. Okay, so compute the one in the first bracket. That's what we have here. You compute the second one, find their product before you find the square root. Then the numerator divided by that answer. So we are getting minus 0.07. 0.07652. Now, After calculating for the correlation coefficient, it's more likely that you'll be asked to interpret it. So we use the interpretations that we give. Minus 0.07 is greater than minus 0.5. So we have a weak or a low negative correlation between sales and cost. If it's weak like this, you can't really use it for prediction. The correlation is not very, very strong. So it's possible that cost will even increase, but you wouldn't see a fall in sales. It is weak. If you have a strong correlation, then the prediction is better. But if it's weak like this, we can't really use it for prediction. Okay, so that's how we calculate the Pearson correlation coefficient. Please, any question? All right, then we look at the Spearman's rank correlation coefficient. See that the assumption under the Pearson is that the data must be quantitative, but we also have qualitative data, data that cannot be quantified. For example, there's an examination, and then someone was first, someone was second. There was a competition. Someone is first, someone is second, someone is third, and all those things. When it happens like that, we cannot use the Pearson's correlation coefficient because those things are ranks. So we can use the Spearman's rank correlation coefficient. Okay, it's not only ranks that we are able to use the correlation, the Spearman's rank correlation coefficient. If the data is quantitative too, we can use it. But as soon as we have ranks, the Spearman's rank correlation coefficient that we have to find. So this one too, it uses bivariate data. So we need X and Y. Now, these are the conditions under which we can use the Spearman's rank correlation coefficient. If both X and Y are quantitative and they have to be nonlinear, okay? And if the two are both quantitative and then nonlinear, we can still use the rank, okay? And then if they are both qualitative, we can also use the rank. So if we have positions for both X and Y, that one too we can use the rank. Or if one is qualitative and the other is quantitative, it doesn't matter. We can still use the rank. But when it comes to the interpretation, it's just the same as the Pearson's correlation coefficient, okay? The interpretation is the same, perfect, strong, and then weak, based on the value that you have. Okay, so let's take one example and then let's see how it is done. But these are the steps in calculating the Spearman's rank correlation. At times in the question, they will just give you the ranks. If they give you the ranks, then you can just move straight away from there. But at times too, if the data is quantitative, you have to find the ranks. So for example, they've given you values for X and Y, like what we use for the Pearson. They're giving you values for X and Y. You will have to rank them, either in ascending or descending order. So for example, if you want to use ascending order, then it means that the smallest number will take the rank 1, and then the highest number will take the last rank. If it's descending order, then the highest number will rather be taking 1, and then the smallest one will take the highest rank. But then you have to be careful, because if you use ascending order for ranking X, you should use ascending order for ranking Y. If you use descending, it must be descending for both. Okay, don't use descending for one and then ascending for the other. As soon as you do that, you get it wrong. Okay. Now, another thing you have to check when we are doing the example, I will show you that if you have repetition of 2 or more numbers, for example, in the data, we have 5 like 4 times in the data. They appeared like 4 times. Assuming that the first 5, the rank there was supposed to be 4. Then it means that the next 5 was supposed to be 5, The next one was supposed to be 6th rank, and the next one was supposed to be 7th rank. But they are all the same number. So what you do is that you find the average of all the ranks. The first one was 4th, the second one was 5th, the next one was 6th, and then 7th. So find the average of all these ranks. So add 4 to 5 to 6 to 7 and divide it by the total number, which is 4. So here, I think you'll be getting something like 5.5 or something. Then you give the 5.5 to all the numbers that you had. So the first 5.5, I'm just giving an example. If the mean is 5.5, then 5.5 for the first 5, 5.5 for the second 5, for the third, and then for the 5th. So if you go to the next number, assuming the next number is 6 or 7, then that one should take a rank of what? 8, since you've exhausted 4th rank, 5th rank, 6th rank, and then the 7th rank. So you have to go to the next rank. Okay.